Hi, and welcome to Module 11 of Lecture 2. In this module, we're going to take a step back from the stuff we did last module and discuss exactly what assumptions underlie the OLS model and, in some cases, what happens when they're violated. So, the ordinary least squares model, or OLS, assumes linearity. It assumes that we can write an equation like y equals a plus beta x, alpha plus beta x, or y equals alpha plus beta 1x1 plus beta 2x2, or however many variables you want. We're assuming we have a linear model. We're assuming that a straight line adequately represents the relationship in the population. If you try to fit this linear model to a non-linear relationship, like the curvilinear ones we saw before, where there's it either curves and it goes downward later, we're going to have biased estimates of our coefficients. What we did not talk about before was the degree to which our model assumes independent observations. Specifically, it assumes that the values on the dependent variable are independent of each other. So if I'm drawing data from my sample at random from a population, each draw, when I measure the dependent variable, should be independent of the next measurement. That is violated a lot in standard political science and social science applications. If I have time series data, then I'm looking across time, and it is very likely that the measurement I get at time 1 is going to be correlated with the measurement I get at time 2. So we're going to have violations of that independent observation assumption. Similarly, panel data, which is cross-section across time, will have similar properties and lead to similar issues. Cluster data, in which you have different groups that have some commonality, also can lead to that problem, because let's say I have like 3 or 4 different groups in a population who have some similarities and some kind of correlated behavior. Then if I draw someone from one group, that dependent variable is going to be more similar to another one from that group than one from a different group. So these cluster data won't all be independent. There are ways around this. We can get unbiased estimates despite these, but the problem is our standard errors are going to be typically biased downwards. So we're going to be more likely to mistakenly reject the null hypothesis. We're going to make more errors. More type 1 errors, more errors which we mistakenly reject the null hypothesis, right? The thing we're trying to avoid. Now, there are ways around this. We won't talk about many of them in this course, but as you go on in methods, you'll see more ways to adjust your standard errors to take into account the structure of your data and the structure of your errors, and the correlation in the errors in particular. You learn words like heteroscedasticity, but that's for the future. Anyway, so in general, things to watch out for. Putting aside the independent observations for the moment, linearity. Do you believe that the relationship between the independent and dependent variables occurs in a straight line? There are some simpler ways to get around that we will talk about later in the course. Outliers. Does a particular case have an unusual value for its dependent variable, given the value of its independent variable? Right. So I see an outlier in our data the same way we saw before, like with the incomes for 25-year-olds. Outliers, which occur a lot, particularly in things involving things like wealth and income, can lead to changes in the mean, as we saw before, and as we saw last time, can lead to changes in the, changes that we don't want necessarily in our measurements and estimates of our coefficients. Leverage is a new term here. Leverage is a case with an unusual value for the independent variable. So we asked, does a particular value for an independent variable, is that very far from the mean of an independent variable? Influence. Does a particular case have high leverage and also is it an outlier? So an influential case is an outlier with high leverage. So it's far from the mean in the independent variables and in the dependent variables, and that can be really real trouble. So let's look at some of this in a second. So OLS, ordering least squares, assumes the relationship is linear between the independent and the dependent variables. So here's a question. What's the relationship between sleep the night before an exam and the grade on the exam? This is fake. So we can do a regression with some data. We get estimates for the constant of about 47 with some error. This t-ratio here has already calculated for you the estimate divided by the standard error. So it saves you a step. Sometimes you'll see the p-value after the t-ratio, and the p-value is basically it's the critical value that you can exceed. It's the critical value that it's the probability associated with the critical value that you can just exceed. So it's the probability of being able to reject, of failing to reject a null, of being wrong. If it's under 5%, we say you're 95% confident that you're not wrong in this case, that you can reject the null hypothesis. Okay. Backing up, the coefficient on sleep, which is the independent variable, is 3.89 from this fake data with an error of 0.84. So its t-ratio is 4.6. That's above 2 and 3. So unless we have very few data points, we're going to say in general, for this fake data, you can reject the null hypothesis that sleep has no effect on grades on exams. Now, for every hour of sleep, since the coefficient is 3.89 and sleep is measured in hours, we expect 3.89 more points on an exam for every hour of sleep. We can plot that here, and we see our model estimates a linear relationship. We have sleep in hours on the x-axis and grades on the y-axis. And we see is a straight line that would predict for us how sleep affects grades for any value of sleep, assuming there's a linear relationship between sleep and grades. But what if our data looked like this? This is a little different from our previous example where the data seemed to fit a line pretty well. Now, there's a lot of points down here, and there seems to be a tailing off over here where the points that are very high don't occur on the line like you might expect, but there are points over here that are uniformly above the line. It's not just like around the line at random, they're actually almost always above the line. When you see data that have systematic patterns away from your line, that's a hint that maybe your errors have a lot of structure still attached to them even after accounting for this linear relationship, and maybe the line isn't really great, right? Maybe it's not a great measure of what you're doing, or maybe you're missing a bunch of important interactions and variables. So we can deal with this potentiality by adding a squared term. So now instead of saying that the grade is equal to a constant plus a beta times your sleep, we add a beta 2 times your sleep squared. Right? We'll get to why that works in next lecture, in lecture 3. But now just understand what the problem is. The problem is we have a lot of points down here under the line, sort of systematically so, and a lot of points down here on the line, systematically so, and a lot of points here above the line, systematically so, and that seems not to be very linear. So we can fit a curve to it, we can fit a squared term to it as well. Now the predicted fit looks like this. It's below the original line up here, then it goes above the original line up here, and then goes below again over here. So now we're capturing a more complex relationship that seems to fit the data better. That's one way we can cope with nonlinearity. How about outliers? Now we have a line that looks pretty darn good over here, but we have this outlier way up here. So we can look at the lines with the variable and without the variable, without the case rather. This top line, this black line over here, the solid dark line over here represents the best fit line, including all the data here. If you pull this outlying variable away, you get this red dashed line. This red dashed line has a steeper slope than the outlying than the line with the outlying variable, and the reason is the outlying variable pulls up the curve over here because it's trying to minimize squared error. This error is very big and it's squared, so this deviation is large and it's squared, so it's going to place a lot of force effectively on the line and pull it up. Right, a lot of influence in the line is going to pull it up from the original line that would have been had this point not been in existence. Does not mean this line is wrong. It means if there's an outlier this far away from the line, you probably didn't get your theory quite right. Either it's not really a line, or maybe this case arises from some different process that's not captured by the line over here. Maybe there's something special about that case, and you really shouldn't include it, right? It's the difference between it's a difference in, say, looking at public opinion during and outside of wars, right? During wars, we have this rally around the flag effect often, particularly early on in wars, and this can lead to higher public opinions than you get outside of a war, and that might alter behavior in ways that it's not good to capture all in the same model. You might want different models during and outside of wars, in which case you want to separate those models. Here, this outlier might occur from some other reason beyond the model's predictions, so you might want to pull it out. That said, you only pull out outliers when you have an absolutely ironclad reason for why that outlying case, that outlying value, isn't really applicable to your main theory. Because once you pull it out, your theory no longer captures that case anymore. Right? You've reduced your scope conditions, you've reduced the external validity of your theory, and are focusing now on everything but that case. So just be aware of that. Outliers can have a strong effect, but you can't necessarily pull them out of your data unless you have a good reason for it. Leverage. In the case of unusual X value, leverage is not always bad. Sometimes leverage is really good. So look at the one on the left over here. Here's sleep and grades, and what we see is we have a lot of data over here, so we can do a good job fitting here, but extrapolation might be difficult to higher levels of sleep because you don't have any data out here. Having a high leverage value in the independent variable that sort of fits with our theory is good. It helps us do a better job predicting the value of the dependent variable grade from sleep in this region over here. However, if this value that has high leverage is like an outlying variable, it's very bad because now you would have had a nice theory over here, but this is going to pull your line way down. So leverage can be bad or it can be good depending on its value. So you get very different straight lines, very different predicted lines, very different best fit lines based on whether or not you include whether or not the high leverage independent variable has a dependent variable value in line with the expectations of your theory of the linear dependency, or very much not in line with the linear dependency. You get very different theories. This one has a lot more error, seems a lot less useful, and doesn't really match most of the data over here, all to make sure this point gets accounted for well, whereas this one does a great job overall. Okay, and to sort of conclude here, if you have a case that's both an outlier and has leverage, like we saw before, that influences the regression line, and that's the example we saw on the right there. It's going to influence the constant and the slope in potentially bad ways. So if you have situations like this, and this is why it's really important to plot your data, if you have situations that are significant, that would exert significant influence, you want to think very carefully if they really are part of your theory or not. Because if they are, your theory might have to be adjusted to account for all the stuff in your theory properly, and a line might not be a very good way to capture that. So for instance, if you had a curve, it might capture this pretty well. So the line might be a bad theory, but the curve might be a good theory here if this is actually an accurate portrayal of what the grades would be for high sleep people. Maybe because they're sick, because they're sleeping 15 hours a day. So that's a different theory, right? One theory would say, I'm looking at this area, and as I sleep more, I do better in a sort of straightforward linear fashion. This theory might say, I increase my benefits on exams pretty strongly for sleep up to a certain point, but if I sleep too much, it becomes maybe correlated with other bad stuff, and therefore I start doing worse on grades, and that will lead to a non-linear relationship. These are different theories. When you have these influential points, these influential cases in your data, you have to think carefully if you should change your theory to account for them more accurately, or, use a different theory rather, or if you should just drop it and say your theory doesn't apply to that case. I should note, just to conclude, if you decide to change your theory to apply to that case, right, you're effectively fitting the data with a new theory. And then if you want to actually test your new theory, you want additional data to test it on. Fitting the data you have and then claiming your theory is supported because your theory came from your data, right, is not a very strong test of your theory at all, because you can always fit your data to whatever thing you make up you want, but you want us to test your theories on data that didn't drive your theorizing. This is what we discussed early on when we discussed inductive logic and inductive reasoning and theorizing. That's it for this one. We're going to go on next to discussing a little more on prediction and some more about errors in our regressions. Thank you very much.